So we'll begin this video with definition 4.56. Let H be a Hilbert space, and let fractor A be a subalgebra of LH. So we say that F in H is cyclic for the family A if the closure of AF equals H, where AF is the image of F under each operator in A. Now, a funny way to think about what it means to be cyclic is by imagining each operator in A as a button that, when pressed, moves H around. So, for example, there's a 0 button that sends everything to 0, the identity button that leaves everything still. And so being cyclic means that if I pick a point, then there's a button that gets me as close to that point as I'd like. Now, for a second definition, we'll say that F in H is separating for the family A if, for every operator in A that sends F to 0, we get that A was actually the 0 operator. So now that this is a particularly powerful property to have, because if A and B act on F in the same way, then we get that A minus B is 0, that is, A equals B. So you can think of F as encoding all the information of the subalgebra A. Now we'll take a look at lemma 4.57. If H is a Hilbert space, and A is a commutative subalgebra of LH, we find that if F is cyclic for A, then that actually implies that F is separating for A. For the proof, suppose that F is cyclic, right? That just means that the closure of AF is a whole space H. And suppose that AF equals 0. Then for every B in A, we have that ABF is BAF because it's commutative, which is B0, which is 0. Therefore, AF is in the kernel of A, but since the kernel is closed, right, then the closure of AF, which is H, is within the kernel. And that means that A is the 0 operator because it sends all of H to 0. Therefore, F is separating for A, and that concludes the proof. In the next video, we'll show some preliminary results about W-star algebras.